Welcome to this explainer. Today, we're doing a massive deep dive into the fascinating and honestly pretty volatile world of nitric acid. Now, if you're gearing up for your 10th standard ICSE exams and you've got your VRFJ Delar or Concise Chemistry books open, you are in the exact right place. We're going to master every crucial reaction, test, and detail of this chapter from start to finish. Let's get into it.
Let's kick things off with kind of a wild question. What liquid is strong enough to literally dissolve solid silver, but at the exact same time is absolutely essential for growing the very food we eat? It's a chemical that has shaped human history in some pretty crazy ways. The story actually starts way back in the 8th century. Alchemists gave it this super dramatic name, Aqua fortis, which translates to strong water. Mostly because, it could dissolve silver. It wasn't until much later that chemical heavyweights like Glauber, Cavendish, and Lavoisier finally cracked the code and figured out its true composition: hydrogen, nitrogen, and oxygen. So here's our quick roadmap for today. We'll meet Aqua fortis, hit the lab for its preparation, skill things up with Oswald's process, dive into its chemical properties, play detective with the brown ring test, and finally look at its real-world legacy. All right, part 1. Let's meet Aqua fortis and check out its physical properties. So pure nitric acid, it's actually completely colorless, but the stuff you see sitting in the lab usually has this yellowish tint to it. That's actually because of dissolved nitrogen dioxide gas, which naturally forms as the acid breaks down just a little bit. And here's a totally wild physiological fact. If it touches your skin, it literally turns it yellow. It reacts with the proteins in your skin to create a compound called xanthoproteic acid. Yeah, definitely wear your gloves. Okay, moving to part 2. Let's head into the lab and see how we actually synthesize this highly corrosive stuff from nitrates. For your exams, you absolutely have to know these precautions. First, we use an all-glass apparatus. Why? Because nitric acid vapors are so incredibly corrosive, they'll just chew right through rubber or cork. Second, we strictly use concentrated sulphuric acid to react with our nitrate. We never ever use concentrated hydrochloric acid. HCl is super volatile, right? Well, nitric acid is volatile too, and we definitely don't want those vapors mixing. We need the non-volatile sulfuric acid to safely push out the volatile nitric acid. And that brings us to temperature control. This is a huge one. Keep the heat below 200 degrees Celsius, and you get a nice smooth reaction yielding your acid and sodium bisulfate, which just washes right out of the glass retort. But let that temperature rise above 200, disaster. You end up making sodium sulfate. It forms this rock-hard crust that you literally cannot scrub out. It can easily shatter your expensive glass setup, wastes fuel, and prematurely decomposes your nitric acid. So keeping it under 200 is the golden rule. Moving right along to part 3, let's take this chemistry out of the lab and into massive industrial production with Ostwald's process. The Ostwald process is a total game changer, and it breaks down elegantly into 3 steps. Step 1 is catalytic oxidation. Ammonia and oxygen react over a platinum gauze catalyst at a blazing 800 degrees Celsius to form nitric oxide. Step 2 is oxidation. We cool that down to 50 degrees where it grabs more oxygen to become nitrogen dioxide. Finally, step 3 is absorption. That nitrogen dioxide takes a bath in water to yield dilute nitric acid. Imagine the journey happening here. 1 volume of ammonia and 10 volumes of air blasting into the catalytic chamber, hitting that hot platinum gauze. The resulting gases then drop down into a cooling tower, shift into the oxidation chamber to turn into that signature reddish-brown nitrogen dioxide gas, and finally shower down the absorption tower. And out the bottom, nitric acid. It's just a beautiful, continuous flow of industrial chemistry. All right, part 4, the chemical properties. This is where we really see its power as an oxidizing powerhouse. There's a really clear pattern to watch for here. Nitric acid isn't your average acid that just quietly pops out hydrogen gas. No way. It's a powerful oxidizing agent. Drop in nonmetals like carbon or sulfur, it violently oxidizes them. Carbon turns into carbon dioxide, and sulfur gets pushed all the way up to sulfuric acid. Meanwhile, the nitric acid itself gets reduced, and it always kicks out water along with that signature reddish-brown nitrogen dioxide gas. Now, what happens with metals? Copper is a classic exam favorite. The whole trick here is the concentration of the acid. Cold, dilute nitric acid reacting with copper gives you copper nitrate, water, and colorless nitric oxide gas. But switch to hot, concentrated nitric acid? You still get copper nitrate and water, but now you get that dense, reddish-brown nitrogen dioxide gas.
The metal's exactly the same, but the concentration totally dictates which nitrogen gas comes out.
But wait, it's not all violent reactions. Here's a super cool exception. Drop metals like iron, aluminum, or chromium into concentrated nitric acid and nothing happens. They become passive. The strong oxidizing nature of the acid actually works against itself here. It instantly creates a microscopic, invisible, and highly protective oxide shield right on the surface of the metal, totally stopping the reaction in its tracks.
Section 5. The brown ring test. Let's play detective and figure out how to prove those invisible nitrate ions are actually in our solution.
This procedure is super delicate. You start with your nitrate solution in a test tube. Then, you add freshly prepared iron-2 sulfate, also known as ferrous sulfate. And yes, it absolutely has to be fresh so it hasn't oxidized in the air. Next, and this is the trick, you tilt the tube and incredibly slowly slide concentrated sulphuric acid down the sidewall. And step 4, do not shake the tube. You want that heavy acid to settle right at the bottom, creating two very distinct liquid layers.
Right at the junction of those two liquid layers, you'll see it. The brown ring. This is your crucial takeaway. It's a highly unstable compound called nitroso iron 2 sulfate. The exact formula is FeSO4.NO. Burn that into your memory for the exam. It's so delicate that if you accidentally shake the test tube, the heat generated by the acids mixing will instantly destroy the ring. Finally, Section 6. The real-world uses and the legacy of this incredibly dual-edged sword. It's literally everywhere. It's used to manufacture the ammonium nitrate fertilizers that practically grow the world's food supply. But it's also used to create devastating explosives like TNT and picric acid. We use it for everyday dyes, life-saving drugs, and modern plastics. And hey, remember Aqua fortis dissolving silver? Well, if you mix 1 part concentrated nitric acid with 3 parts concentrated hydrochloric acid, you create aqua regia. It's a mixture so intense it can even dissolve noble metals like gold and platinum. So, as we wrap up this explainer, I want to leave you with this final thought. How wild is it that a single chemical molecule can simultaneously hold the power to feed the entire planet and the devastating potential to destroy it? Chemistry really is the ultimate double-edged sword. Thanks for hanging out with me to master this topic. Keep studying hard and keep that curiosity burning.